logarithm functions. So we've seen that anytime you have a log with the same base, or like a power going to the power of the base, they cancel each other and you get x. Well, if you think about that, you have a log function, exponential function, you plug one into the other, they cancel each other out, and you just get x. That's a definition of an inverse. And that means logs and exponential functions are inverse of each other. And why is that important? Because that's so that since we know what a graph of an exponential function looks like, right? This is a decay graph. This is a growth graph. If we graph the inverse, where we draw the dotted line right here and spin it across, we get our log graph. Right, so this is a log of a growth function. Right, that's probably this is the classic log graph you see, and then this is a log graph of a decay function. Notice how it's dying. This one's growing. You don't see this one as often, but still the same concept. If your base is less than 1, but greater than 0, and if our base is bigger than 1, it's the same concept. If your base is less than 1 to decay, if your base is bigger than 1 to growth. Now again, this is probably the main one I want you to know, because this is the most common log function. So that's one way to graph the exponential functions, which you know how to graph, and then find the inverse. Another way to graph these is, well, just kind of memorize these log functions. And we could use the information we know about these to help us with those. Remember when you do an exponential function? If I give you something like y equals a b to the x plus k, our k here was our horizontal asymptote. Right, there's a dotted line that we couldn't cross. Now when you do the inverse of it, that flips to right here. And it's actually stuff inside the log that's horizontal. That's a vertical asymptote. The vertical asymptote is at x equals h. Right, so it all comes from the fact that it's the inverse of this function. So the x and the y switch. Over here we had y equals k, horizontal asymptote, and now we have x equals h is our vertical asymptote. Let's use that to look at the basic graph of a log function. So let's like that. A basic log equation, like log base b of x, looks like this. So we have a vertical asymptote at x equals 0, because there's nothing here. So that's up at 0. Our initial y-intercept is at 1. So it's kind of like before, where the a in front that lets you know the initial y-intercept is at 1. And then the graph kind of just looks like this. My domain would be, if you look at the graph, it starts at 0, goes on from 0 to infinity. And my range would be negative infinity, positive infinity. If you look at the graph, top, lowest arrow, highest arrow. So all real numbers. So that's what an exponential graph looks like. That's what log graph looks like. Now if you notice, the domain and range particularly, that's the exact reciprocal of the domain and range of an exponential function. Look the one right here. My domain is all real numbers, and my range is 0 to infinity. So remember, these are inverse to each other. When you do inverse, you just switch domain and range. That's why it looks like this. So one way to do it again, you could just graph an exponential function and then find the inverse. But in general, that's what log function looks like. Something like this. So let's do another example real quick. What if I gave you log 3 log x minus 1? Something like that. Well, in this case, my vertical asymptote is at inside opposite x equals 1. My a is 3, so that just lets me know how far I should go from my vertical asymptote to find my initial point. And then we just graph it. So at 1 point my vertical asymptote, right there, and then 3 away. My a is, I think 3, so I'm gonna go 3 to the right of that to find my initial point. The graph just grows up. Some to that effect. So that's how you graph a log function. So let's move on to our first row example here. So consider a function 2x minus 1 plus 1. State the transformation that maps the basic log function to y equals f of x. Find domain and range. Find the asymptote and axis intercepts. Sketch the graph of the function. Find the inverse. Okay, so A. State the transformation. Right, so this thing never changes. Inside opposite, outside follow. Right, so my x I'm going +1, and on my y, follow, go +1. So 2 ways to write this. You can write the vector 1, 1 transformation along 1, 1. Or you could say shifts up 1 and right 1. Right, either way. Find the domain and range. Well, it helps. I like to graph it before I find the domain and range. I can do the domain and range from here, but I prefer to do it later. Find any asymptotes or intercepts. So when we find the asymptotes, so vertical asymptote, inside opposite, right? So it's just right there. So x equals 1. If they want axis intercepts, we do those always the same. That thing never changes. You want the x-intercept. You set y equal to 0. So to me, 0 equals log of 2x minus 1 plus 1. And all we have to do is solve that. So subtract 1. So I get -1 equals log base 2 of x minus 1. The way we solve this, you take the base of both sides. 2 to this side, 2 to this side. So I get 2 to the -1 equals, cancels out, x minus 1. So it's this 1/2 equals x minus 1. Add 1 to both sides. X equals 1.5. So that's my x-intercept. 1.5 and 0. You want the y-intercept. We're just going to set x equal to 0. Remember, x and y-intercept never change. No matter what problem you're doing, x and y-intercept are constant. X-intercept set y equals 0, y-intercept set x equals 0. So you just got to plug 0 into this equation. So y is an equal log base 2 of 0 minus 1 plus 1. So I get log base 2 of -1 plus 1. Now you can never evaluate log of a negative number. So this is actually not possible. So none. There's no y-intercept. So we have our vertical asymptote. We have our x-intercept. And they want us to graph this. Okay. So I'm doing like that. Our vertical asymptote is at x equals 1. And we're going to cross at 1.5. So here's my vertical asymptote. Now normally we'll cross that 1 to the right of it, right? My a is 1. But there's a shift here. So like it's kind of go like you cross 1 to the right, but then you have to move it up 1. So in my head, like there's a point right here where it normally would cross. Right? So we'd go like this normally, but then we have to move it up 1. And that's why we have a y-intercept of 1.5. So my graph's kind of like this. Which makes my domain 1 to infinity. And my range, all real numbers. So there we go. Find the inverse function. Now, this is find it, not graph it. So they don't want us to graph the inverse function, which means we just flip it across there. They want us to find it. So if you want to find the inverse function, kind of run that space, so do it up here. Right, so inverse switch x and y. So this would be y and x, so we're going to switch it. X equals log base 2 of y minus 1 plus 1. Okay, let's solve the inverse. So subtract 1 from both sides. Got to solve for y here. X minus 1 equals log base 2 of y minus 1. Now remember, the way you get rid of a log is you take the base of both sides. So we're going to take the 2 to both sides. This cancels and we get 2 to the x minus 1 equals y minus 1. And then we just add 1 to both sides. 2 to the x minus 1 plus 1 equals y. Like that. And that's our inverse function. Now if I wanted to graph it, that's actually something we're really good at graphing. I'm going to do it right now because I know how to do it. You go to 1, dotted line. That's right. That's our horizontal asymptote. We normally would go cross 1 above that, but we got to move it to the right one. So it's going to be more like this. Like that. Right? If you look at the asymptote, if you look at the y equals x, that's a perfect inverse. So there we go. Next one. For each of the following functions, find the domain and range, find the asymptote. So we're just going to graph this. Okay, so again, I always like to do domain and range after I graph it. So let's find any asymptotes and axis intercepts. So my vertical asymptote on this one Inside opposite, x equals -1. If I want to find my intercepts, right, so I have to find the x-intercept, y equals 0. So I'm going to go 0 equals log 3x plus 1. Now, what you do here is you try to get rid of the log, so you take the base of both sides. 3 to 0, 3 to this. X plus 1 on this side. Now, a lot of people confuse this. 3 to 0 is not 0, it's 1. 18 to 0 power is 1. Subtract 1. And x equals 0. So it's my x-intercept is at 0. That's probably my y-intercept also. Y-intercept. Right? So you set you plug in x equals 0. So you have log base 3 of 0 plus 1. So you get log base 3 of 1. Anytime log equals 1, anytime log the base of 1, it's automatically 0. Because 3 to the power equals 1, 0. So there's my x and y intercept, 0, 0. Okay, so we have that. We have a rook asymptote that wants to graph this. My asymptote is at 0. My rook asymptote is at -1, and my y-intercept is at 0, 0. So we're just gonna graph it. It's a log function. Looks kind of like this. So there we go. My domain would be -1 to infinity. And my range would be all real numbers. So there you go. Solve f of x equals -1 algebraically and check your solutions to your graph. Okay, so let's erase this. I don't need this anymore. So they want to set our function equal to -1, and they want us to solve it. So remember the way you solve a log function, you take the base of both sides. So you get x plus 1 equals 3 to the -1, or 1 over 3. And then we subtract 1. So x equals 1/3 minus 1, which is the same thing as saying common denominator, -2/3. X equals -2/3. Check the solution on your graph. So they're saying, hey, if you went y equals -1 on your graph, would it hit -2/3? About. It's not perfect, but right there, yeah. Find the inverse of f of -1. So now we got to find the inverse. So let me erase the graph because I don't have space. So if you want to find the inverse, we're going to switch x and y. So it's essentially y, this is x. So let's switch x and y. That should be a y. And you just got to solve for y. So if you want to get rid of a log, take the base of both sides. These should cancel. You get 3 to the x equals y plus 1. And we subtract 1 from both sides. And there's our inverse. Okay, last thing. Kelly says that in order to graph y equals natural log of x squared, you could first graph y equals natural log of x, and then double the distance of each point on the graph of the x. Is Kelly correct? Check your answer. Yes, she is. Right, you can see here, right? It is double. But why is she correct? Well, don't forget our rules of logs. Y equals natural log of x squared. What's one of my favorite rules of logs? Is you take the power, you can move it to the front. So y equals 2 natural log of x. So it's literally just 2 times the graph of natural log. That's why Kelly's correct. There we go. That's the lesson.